Hello, dear students. So this is our second lecture on these complex functions. So if you remember that in our previous topic we have discussed about what's basically why we use these complex numbers and what are the applications of these complex numbers in real life. So you can find that. So you just check my first this lecture on these complex numbers. So you will find that so it has wide applications in real life, even engineering, even in mathematics, or even you talk about the computer science. So it has a lot of application, right? So today's topic is about if you talk about the complex analysis. So that means so the basis is it's coming from these when you talk about these complex analysis. So that means you are dealing with the complex functions here, right? So one of the concept, if you so one of the concept basic concept in this complex this function is that we have analytic function, right? So analytic function is that if we because we are working in the complex plane, so we are saying that this function can be called an analytic function if we consider some point in the complex plane, right? So suppose we have some point here, so this is some complex function here f of z, right? And so real axis and so imaginary axis, right? So this is a complex function in this complex plane, and I'm saying that this function f of z can be called analytic function if we consider choose some point z equal to z naught, right? So we are choosing some point, we choose some point here z naught. So at this point, we're saying that if in the at this point, so if in the neighborhood of this point z naught, the function will be differentiable, right? And it should be differentiable at z naught itself also, right? So that means when it has differentiability in the neighborhood of some particular point, we can say that our that complex function can be called an analytic function, right? So you are familiar with this thing. So because mainly I will focus on the problems related to these topics, and so this is basically how we can define a complex function. This sorry, analytic function, right? Now, so there's a test which is basically helps us to calculate whether a given function we can have some exponential function, any polynomial function we can have. So you can check the analyticity of that function. So with the help of this Cauchy-Riemann condition, right? So this is that Cauchy-Riemann condition. It tells us that if we have a function, we have this f of z, it can be written as some u plus iota v, right? But u of x is basically is a function of x and y because we can say that we are writing that z equal to x plus iota y, right? And this f of z, so you can write it this way also. That's u of x plus iota v of x, right? So because these are basically functions of those the real and the imaginary parts of that complex number, right? So this is x and y because we can write the complex number in this way, or you can write it in this form, right? Now, so the Cauchy-Riemann condition is that if you can choose that the partial derivative of this function, the real part of that complex function, because this is our complex function which lies in some domain D, we have some range, and so if this condition is satisfied that partial u by partial x is equal to partial v by partial y, and second if partial v by partial x is equal to minus partial u by partial y. So in that case we can say that that function we can say then f of z will be analytic in that case. Right? So this is so it will take whole lecture. So if I talk about this Cauchy-Riemann condition, we can you can check its proof also. Maybe some materials available on the net, right? But mainly we'll focus on the problems related to these analyticity to check the analyticity of a given function, right? Now, so there's suppose we have some problem here. We need to check whether the given function is analytic or not, right? So we have this exponential function, and we need to calculate that. So we need to check whether this function can be analytic or not. So that means it should be differentiable as well as defined, or it should have some single value function, right? So in that case, we can write that we can write that the complex function can be written as that's right. So we are writing complex function in that way in this fashion, and we can write the what's our u of x, y, or u can be equal to u is equal to right? So these are basically the u and v parts because Why we need these things? Because we need to check this CR condition, that is Cauchy-Riemann condition. It tells that if this condition is satisfied, these two conditions are satisfied, so we can say that the function is analytic. Because in this problem we need to check the analyticity of a given function, right? So whether this function is analytic or not, right? So first we first write that, because we can write that complex function in this form u of u and v, and you can check by comparing these two equations, right? So you can write u of x will be this one, and v of xy will be this one, right? Now, first condition is that if you write now partially by partial x, right? So calculate partially by partial x from here, because this is partially, you need to differentiate it partially, right? So this cos y will be constant in that case, so this will be minus cos, okay, right? And similarly, if you calculate now partial v by partial y, so that will be equal to, so differentiate this with respect to y now, so this will be minus e power minus x, okay. Similarly, second case is that if you calculate now what is our that partial v by partial x. तो पहले हमने फर्स्ट कंडीशन हम देखेंगे, because partial by partial x equal to partial v by partial y. So first that Cauchy-Riemann condition is satisfied, right? And similarly we will see that whether the second condition is satisfied or not. So for that case we need to calculate first that's partial v by partial x. So that's equal to e power minus x. And from here, you write now what's partially by partial x, partial one. That partially by partial y will be minus times e power minus x. Okay. Okay. So this is clear because we have calculated this. So because first condition is that this partial u by partial x should be equal to partial v by partial. So this is very clear because okay, so I did some mistake here, because when you calculate this, okay, so this is clear because this should be equal to this one, right? So because e power minus x cos y, this minus e power minus x cos y. So that means partial v by partial x should be equal to partial v by partial y. So from here you can say that partial u by partial x by partial. Okay, so first condition is okay because we are calculating that. Okay. And similarly, if you calculate now, you check, now compare these two. Partial v by partial x is minus times here, right? So you can write then, so you can write that partial v by partial x, that's minus times partial v by partial, right? So that means both these conditions are satisfied for the given function. So we can say that the given function is analytic. Right? So this function is analytic, right? So that means you are saying that this function is differentiable and single value. It is well defined and differentiable, right? So this is how you can check the whether the given function is analytic or not. And similarly, if we write one more problem, suppose we have this, we need to check that f of z equal to, okay. So we need to check whether this function is okay. So we need to check whether this function is analytic or not, right? So again, so first before that, because we have some real values of that z square, right? And similarly imaginary value of z square, right? So I can write now. So I can write here what's our z square here. So z square can be written as, that will be x plus I over 1. Okay, right? Because I can expand this z square in this form, right? Now So this is absurd is basically the real values of that z square. The real value of this is equal to x square minus y square, right? Because it is a mu plus iota v form. So it is a mu plus iota. So this is a, sorry. So this is a real part of that this given complex number. And similarly, we have this iota multiplied over second term. So this is our the imaginary part of the given complex number, right? So we can write them. So this f of z will be there. So f of z will be, so that will be equal to, so what is the real value of this? So that will be x square minus y square plus minus that iota into 2. Okay. Now you compare this. So compare this equation. You have this. We can write this complex function in this form. That's u of xy. Okay. So which says that our u of xy will be, and our v will be equal to, because, is it okay? Because our imaginary of this is that's 2x. Okay. Now let's calculate now. So we need to check this condition whether this condition is satisfied. So we need to check the condition that, okay. So we need to check this condition. So for that case, so let me rewrite this. What's u of x and v of x? We can write what's u here. So u is, that's x square minus y square, and our v is, that is minus 2x. Okay. So let's calculate now what's partial u by partial x, and what is partial v by partial y? So that's equal to, when you calculate partial v by partial y, so that's equal to minus 2x. Right? And similarly, you need to check that. So you can calculate what is partial that u by partial y, or you calculate first to partial v here. So that is to write orderly, because we need to calculate this condition partial v by partial x. So that's partial v by partial x. So that's equal to minus that 2y, and what is partial u by partial y? So that's equal to, that's minus 2. Okay. So you can check, because if you compare here, so that partial u by partial x equal to minus times partial v by partial, right? And from here, so you can check that partial v by partial x equal to partial u by partial. Right? So that means the given function is not analytic, because our CR condition, Cauchy-Riemann condition are not satisfied, right? So we can say that the given function is not analytic, right? And similarly, if you have one more problem, if you talk about now, if we want to examine the nature of the function, if our given complex, if we have some complex function, we need to check the nature of that function at some z equal to 0. You can say that, right? Whenever x equal to y in that case, right? So let's right now. So one more problem is that we need to examine that. We need to examine the nature of the function, and the function is our, that's f of z, that's equal to, okay. Okay. So this was function for z not equal to 0, right? So we need to check that. So we need to check that this f of z equal to 0. Here f of z equal to 0. F of z equal to 0 for z equal to 0. Right? So that means we need, because f of z is non-zero, so it has a value for z not equal to 0, but f of z will be 0 for z equal to 0, right? And we need to include, because we need to check the nature of the function. So in these two cases, right? So we need to include the origin also. So you can say that in a region. So you can say that in a region including, right? So we need to check that nature of the function, right? Okay. So first let's calculate now. Okay, let's write now. So we can rewrite this equation because we have that f of z. So that's equal to that x square, or you can write this as x square so this we can rewrite as that's x cube y raised to power 5. Okay. So I simply multiply here, right? That's because when you take that x square y raised to power 5, you multiply that term to this one, so you can get this thing. Okay. And simply that solving this bracket, right? So you can check that this is some u plus iota v form, right? Because I can rewrite this as, so this will be some u plus iota v form, right? So that means I can rewrite this as, that is, so f of z will be equal to, that's x cube y raised to power 5 upon iota. Okay. So this is some, so this is u, ये हमारा u है and this is v. Okay, because u is a function of x and y, and similarly v is a function of x and y, right? Now we need to check, let us calculate the differentiability, because in order to check the analyticity, so in order to check whether the function is analytic or not, तो उसके लिए हमें क्या करना, we need to check the differentiability. So first we put that, if we put that at z equal to 0 first, right? So we can say that what's f dash of 0? So that will be equal to, so that is limit z tends to 0, that's f of z minus f of 0 upon, that's equal to that z minus 0. Okay. Or this will be equal to, okay. Now because f of z is known to us, right? So just substitute that value. So f dash of 0 will be equal to, so that will be equal to, you can add that x square y raised to power 5 x plus iota y. because why I'm writing, because f of z is our this thing, right? So f of z हमारा इतना है and z is basically x plus iota y, right? So that's why I multiply here, divide by x plus iota y, right? And you can see that this term will cancel, right? And we get here that x square y raised to power 5. Okay, so this is our f dash of 0, right? And that limit z tends to 0. And again, you can just do one thing, that so you can have that limit. Okay, so this is very clear because limit z tends to 0 here, and this is that f of z by z. Okay, now let's choose, now let z tends to 0 first, right? And that, so we have two cases here. First we will choose that let z tends to 0, right? So along the path y equal to x. So that means we have this complex plane, right? And we have this real axis and this imaginary axis, right? I'm saying that we have some complex function here above that, right? And we are saying that because you can vary this, you can vary this. First, putting that z tends to 0 and y equal to x, because on this line, the line which is crossing to the origin, so we have a y equal to x on this. Right? All the values are equal, right? And in that case, so we can say that. So first is that when you z tends to 0 along the path y equal to x, right? So what will be our value? So we can write them. So what's our f dash of 0 in that case? So f dash of 0 will be equal to, that will be limit, because y equal to x, right? Or you can write this as this, because I am saying that z tends to 0, so you can write that limit x tends to 0 here, right? And that x square y raised to power 5 upon, that is x raised to power 4 plus y raised to power 10. Just check that, because we have this equation that's limit z tends to 0, x square y raised to power 5 divided by x raised to power 4 plus 5 plus y raised to power 10, right? And I am choosing here that if you put z tends to 0 along the path y equal to x, so that means हमारा y x के बराबर लेना है, because I need to choose different paths. हमें देखना है कि जो whether this derivative exists by choosing the different paths from point from some point z to z naught, right? So first is that when you put y equal to x here, right? So this will be equal to, you know, that limit x tends to 0. So this will be x raised power that x raised power 5, okay? So x raised power 4 plus y raised power 10. Right? So this will be equal to 0. Right? So in that case, our dash of 0 will be equal to 0, right? Because x tends to 0, right? And similarly, second is, again I will choose now here. Again I can say that let z tends to 0, but I am choosing different path. So first, पहले path में हमने कहा कि when y equal to x and limit z tends to 0, and again I will put that z tends to 0. Now I can say that this y square y raised to 5 equal to x square. We can have different paths now, because if you take the different values of the x and y, so I'm choosing some different paths from, it can be this way or any, right? So I'm choosing different paths and check the differentiability of a function, right? So first is that, first case was this thing, and here f dash of 0 is equal to 0. But second case is when you put that z tends to 0, but y square x square equal to y raised to power 5, right? So in that case, our f dash of 0 will be equal to limit that x tends to 0, and this will be equal to x raised to power 4, x square into x square divided by x raised to power 4 plus x raised to power 4. Right? Why? Because x raised to power 5, so this y raised to power 5 equal to x square. So this will be x square, and instead of y raised to power 5, मुझे लिखना है x square, right? And in the denominator x raised to power 4 plus this should be x raised to power 5. X raised to power 5 raised to power 2. So that is x raised to power x square raised to power square. So that's x raised power 2, right? And this will be equal to, so this will be simply limit that x tends to 0, and this will be x raised power 4 upon x 1 by. So just check the two cases. तो पहले केस में हमने क्या किया, अगर हम चूज करेंगे कोई पाथ y equal to x and limit z tends to 0, in that case our f dash of 0 equal to 0 in that case, right? In second case, I'm saying that I'll choose some now different path where our x square equal to y raised to 5, and putting that z tends to 0, right? So in that case, I will get now f dash of 0 is 1 by 2 here, right? So that means the limits for the two cases are different here, right? So just check that, because we can say that this f dash of 0, so we have two cases here. So first case is that it is 0 if I can write, okay, you can just write y equal to x, and it is equal to 1 by 2. So we have two cases. First case we are getting some differentiation, that's f dash of 0 equal to 0, but in second case I am getting 1 by 2. So that means the limit is not unique here. So limit is not unique here. In first case limit is different, and second case we have two different limits, right? So we can say that. This f dash of 0. So we can say that f dash of 0 does not exist. So that means differentiability of a given function does not exist, because we can, by putting the same limit and choosing some different values, I am getting some different function, because final function will be same. So first case में हमारा आता है when you put y equal to x f dash of 0 equal to 0, but in second case I am getting some value 1 by 2. So that means जो हमारा limit है, when you put the limiting values, the limits are different, right? I'm not getting same limit. So that means the differentiation. So from the basics of that limits and the derivatives of a given function. So when the limit does not exist, we can say that the differentiation f dash of 0 does not exist. So that means our given function is not analytic, right? So including origin also, right? So including origin, it's not analytic function, right? So this was all about how to check the analyticity of a given function with the help of this Cauchy-Riemann condition. Or in coming lectures, we'll also talk about some new problems, like if you talk about that we have this Cauchy-Riemann condition in polar form also. So that means if we have some given function e power iota theta. So because in that case you need to take the variation with respect to that r and theta, right? So we can also write then this Cauchy-Riemann condition in polar form also, and in our coming lecture we also take some problems from that Cauchy-Riemann condition but in polar form, and some another problem, like if we talk about that if we have one part of the given function is given, like real part of a given function is given, so we can calculate the total analytic function for that in that case, right? So hopefully we will discuss that in our next lecture. Thank you very much.